Would you be willing to put everything on the line to play this game?
You are given a fair two-sided coin and you flip it until you get your first heads. So in this example we have tails first, and then we get another tails, and then finally on the third go we get the heads that we were looking for. So altogether that was 3 flips, and this game gives you 2 to the power of 3 in prize money. So that's 2 to the power of 3, which is £8 won in this example. Now, in this next example, we get tails first, and then we get the heads. Okay, so that's 2 flips altogether. So our prize money is going to be, well, it's 2 to the power of the number of flips. So in this case, it's going to be 2 to the power of 2, which is £4. And in general, the same method applies. We flip a coin so many times until we get our first heads. Let's say we flipped n times, and then our prize money in this game is going to be 2 to the power of n.
So, how much would you be willing to pay to play this game?
£3.
£5, maybe 10 if I'm feeling adventurous.
154. No, 100. No.
That's how much.
£90.
£2.
£2 because then I can't lose anything.
Now let's go ahead and answer this question mathematically. So I've defined a random variable x to be the amount of prize money that I get back on each game. X is a random variable, so we can work out various properties of it, like its expectation. And why are we doing that? Well, perhaps the question of how much would you be willing to pay for a game is the same question as, well, what's the expected return on that game? Okay? And how do you define expectation? Expectation is, it's a sum, and it's a sum over the possible values of x, right? The possible prize monies times the probability of getting a specific prize money. Okay, and this is a sum from, what's a sum from 1 to infinity, right? There's infinite amount of possibilities. Theoretically, we could flip the coin forever. And now let's just work out this explicitly. So, the first case is we get heads on the first flip. That happens with probability half, and our prize money from that is 2. Well, what if we get heads on the second flip? That happens with probability half times a half, which is half to the power of 2. And then, well, our prize money from that is going to be 2 to the 2. Okay, it's 2 to the power of the number of flips until our first head, and including the first head. And then we can just continue this pattern. Okay, the expectation is as follows. Times 2 to the 4 plus ... and it carries on forever. Okay, well now you might see something amazing happens, absolutely amazing. These things cancel. Okay? And we're left with 1 plus 1 plus 1 plus ... And what is this? Well, this is infinity, right? 1 plus 1 plus 1 plus 1 plus 1 grows without bound. Okay, and that's the surprising thing. The expectation is infinite. So you should be willing to pay everything you earn for the chance to play this game. Or should you? This game is called St Petersburg Paradox. It's a paradox because despite its infinite expectation, few people will be willing to pay more than £10 to play the game. It derived its name from the city in Russia, St Petersburg, where the great Daniel Bernoulli lived and once analysed this problem. So, is there a solution? Well, first of all, there is no trickery. The expectation of this game genuinely is infinite. I thought it'd be quite interesting to program this problem, so here's a simulation of 1,000,000 games. As you can see, the average prize money, averaged of all 1,000,000 games, grows slowly but surely, powering upwards towards infinity. Note that the y-axis isn't the total earned, it's the average prize money, each game averaged of all 1,000,000 games. So why then? Why would no one sell their soul? Heck, even pay £10 to play a game with infinite expectation? Let's look at the answer offered by Daniel Bernoulli. Daniel said that we shouldn't base the value of a game purely on the expected amount of prize money, but rather the expected utility or usefulness that it brings. Using expectation alone can lead to some pretty crazy results, and we should take into account the subjectivity of money. Like in this example. What Daniel Bernoulli really meant by utility is the idea that money has subjective value. Okay, let's illustrate that through an example. So here is Steve, my beautiful, beautiful assistant. Right, and I gave Steve £1,000,000. Before this, Steve was homeless, right, and now he has £1 million. But I offer Steve an amazing opportunity, okay? An investment opportunity like no other. We flip a coin, if it comes up heads, well, I'm going to times Steve's money by 4. Right? Times it by 4. And if it comes to tails, well, unfortunately, Steve's going to lose everything. Okay, now it's going to be a simple calculation. We can work out the expectation. Right, the expectation is, if I times his money by 4, but he already had $1 million, then he's going to gain 3 million. Okay, and that happens with probability half. And then if he loses it all, well, he's going to lose $1 million, and again that happens with probability half. Times minus 1 million. Okay, now this is a simple calculation. It's 3 halves minus a half, which is 1 million. The expectation of my investment opportunity is $1 million. Well, Steve should obviously take it. But he wouldn't, right? That doesn't make sense, that doesn't fit our intuition. Why would Steve risk losing everything, losing the £1 million that he's never ever had in his life before, for the chance to gain more? So, what should we use instead of expectation? Well, how about we use the expected change in utility? Now you can just think of this as, how much happier am I going to be by playing the game? Well, of course it's going to be a function of how rich you already are, your wealth, and also the cost of the game. How much you have to pay to enter the game. So how does this thing work? Okay, so let's fix W. For me, let's say W, my wealth, is £100. And then let's vary C, the cost of the game. As soon as C gets too large, and this thing becomes negative, well then, it's no longer useful for me to pay that much money to play the game. I expect to be sad if I play the game, right? I expect to have negative utility. Let's have a look at a few examples.
Now let's plot the expected change in utility, which remember was that infinite summand from earlier. Here, wealth is fixed at 1 million, and we see that past around £21, our change in utility becomes negative. In fact, a millionaire should pay at most £20.88 to play this game. Here's a similar graph to before, but now wealth is fixed at £1,000. In this case, someone should pay at most £10.95 to play, before the change in utility becomes negative.
Okay, so let me break down the formula in a bit more detail. It's still an infinite sum, and the probabilities are still the same. But instead of working out the amount of prize money, we're working out the utility of those prize monies. Okay, we have natural logs here. Why do we have natural logs? Well, the gradient of a natural log graph is decreasing. So this takes into account the diminishing utility of money. And then inside the natural log we have your original wealth plus your prize money minus the cost of the game. So altogether this is going to be your wealth after the event, right? After you receive the prize money. And here we have W, which is just your original wealth. And now I've just combined this into one natural logarithm here. And the claim is that this converges for all values of W and C. Well, let's go ahead and try and prove that. For that I'm going to do this in red. So, first of all we can say that this is going to be less than or equal to the same thing, but let's just get rid of the minus C of W. And then we see that what we have inside the natural log looks a bit complicated. It would be easier if we could introduce an exponential. Well, that's easy enough to do. 1 plus 2 to the I of W is in fact going to be less than e to the I, but we don't know for what I that's going to be true. If I is big enough, then that's definitely true, but we're not quite sure where it begins. So let's just say for I bigger than n, some big natural number. Well, now we have the finite sum up to n minus 1. Okay, this might be a little bit confusing, but it'll make sense when I write the next bit. And then we have the infinite tail, but now we're starting from I equals n. And why are we doing that? Well, we're doing that so we can introduce the exponential. Okay? Because past some big n, this thing inside the bracket is less than e to the I. Okay, well that's why we introduced the exponential in the first place, so that we can cancel these two things. The natural log of e to the I is just I. Right? It's just I. And now let's try and prove that this thing converges. And if we can prove that this thing converges, then the original thing converges by the comparison test. Okay, so this thing is screaming ratio test to me. So let's go ahead and use that. We want to consider the limit as n goes to infinity of the ratios of the things that we're summing up. So we want to consider that the limit as n goes to infinity of a n plus 1 over a n. Right? Well, a n plus 1 is going to be we're using a different index. It's going to be n plus 1 on the top, and then on the bottom we're going to have 2 to the power of n plus 1, and then we're dividing it by a n. What's a n going to be? It's going to be n over 2 to the n. Let's combine this into one fraction. We're going to get n plus 1 over n, and then we're going to have 2 to the n on the top and 2 to the n plus 1 on the bottom. And then some things are going to cancel here, right? We have powers of 2, so let's just combine these. We can rub out the thing on the top, and we're just left with 2 on the bottom. And now let's take the limit as n goes to infinity. Well, that's easy to do. This thing, n plus 1 over n, goes to 1, and 1 over 2, of course, it just goes to 1 over 2. So overall, the ratio goes to a half, right? And this is less than 1. So by the ratio test, this thing right here converges. So we have something finite plus something else that's finite. So the entire thing converges, and therefore by the comparison test, our utility function converges for all values of w and c. So there we are. Have we resolved the problem? So, is the infinite gap between the actual expectation and the amount of money that people would be willing to pay best explained by the diminishing utility of money? Well, perhaps, but there are some practical issues to St Petersburg Paradox anyway. For one thing, you can only flip a coin finitely many times, because, well, eventually you're going to die, and the person that offered you the chance to play the game, they're going to die. And no one could offer you the chance to play the game in the first place because, well, people only have a finite amount of money to give away. So, do these things resolve St Petersburg Paradox? Absolutely not. We can resolve these three issues in quite simple ways. For one, instead of money, let's just use points, okay? Imaginary points, and these points can be infinite in their supply. Second of all, to resolve the issue of the diminishing utility of money or points, well, let's just state that our goal is in fact to maximise points. Thirdly, to resolve the issue of the time it takes to flip a coin, just imagine instantaneously receiving the amount of flips that it took to, receive a head. Now, with these three postulations, I give you the chance to play St Petersburg game as many times as you like. But each time it's going to cost you, let's say, 1,000 points. Would most people play if their only goal was to maximise points? No, they wouldn't. So St Petersburg Paradox is still alive. How do we explain this then? For me, it comes down to the fact that humans are finite creatures with only finite concepts of space and time, and thus we can't truly comprehend St Petersburg Paradox in its infinite glory. And thus, St Petersburg Paradox is still alive and well, there is no solution.